There we
Bill is
go.
going
Got
to have
sound.
to unmute. Yeah, there we go.
There we
Thank you.
go. There we go. We are now in business. All right, Bill Ragsdale, P6KN, and I'm the founding president of the Fourth Interest Group below these many, many years. And then I faded into oblivion as the technology passed me by. So today we are going to investigate what I gleefully title as the road trip conjecture. So, uh, 2 days ago, with my bride on our 54th wedding anniversary, we took a ride in the countryside here in Yolo County and went to the west to a small town called Cape. And in there is the Road Trip Cafe. And sitting at the table at the Road Trip Cafe, there were a number of photographs laminated and little historical segments and all. And I saw somehow a clipping that had this formula on the table. It was the 11111 times 1111 equals. So we see this number that's a sequence of digits from 1 to 9 and then from 9 back to 1. And I thought, no, that's interesting. Um, I began to think about it at the table there and wrote it down and came back home. And I said, I'd like to investigate this. So it's a sequence of digits. I know that 1 squared is 1. That's easy. And then I also know that 11 squared is 121. So then the conjecture uh, is the square of 111, 1, 2, 3, 2, 1. And since 100 squared is 10,000 and this other number is 12,000, so it's in the right range. So I thought that is likely. And so then the question is, does that pattern hold for all similar squares up to this one that is our example? And so that forms the conjecture, the road trip conjecture. So here's my investigation. First, I quickly wrote a one definition program, about 3 lines of the do loop and with numbers and incrementing and squaring and printing. And I thought I was done. Well, no, big surprise, learning experience, because as one would expect, there were 3 or 4 flaws within that one definition. So then I had to stop and back up and then write it in modules and then test the modules. And then I had to go back and learn or discover some of the fundamental resources that were available. I was beginning to do everything by double numbers, and then I realized there was no double number multiply in Win32 because if you multiply 2 double numbers, you would get a quad. You would get something that's 4 cells wide. And to my surprise, it's not there. And then I realized, no, you've got some overflow problems when you're doing these large multiplies. And so the largest multiply that they have available is a mixed mode, M star or M times, which multiplies a single times a single for a double. And this is 32-bit fourth. So you multiply 2 32-bit singles and you get a 64-bit double. And that, it turns out, is the building block. Now, it turns out also there is a triple precision multiply. Digging deeply in there, I found out there is a multiply that will take a double times a single. So you take a 32-bit number, a 64-bit number times the 32-bit number, and you get a triple. You get a number that's 3 cells wide. But that was not at all useful for this application. So I'm going to work around the good old M star. And along the way, in doing formatting, I stumbled onto the fact there are about 10 different numeric outputs with a variety of formats that are predefined. And one that was quite interesting was the UD comma dot R, which means take an unsigned double delimited by commas and then print it in the field R digits wide. And that became the cornerstone of my output. So here are the 2 support words. One of them is a mixed mode square. It takes a integer, 32-bit integer in and squares it to a 64-bit double D1. And then to increment, in this case, each time we're taking a decimal number and we're appending a 1 on the digits, integer side, digit side. So we multiply by 10 and add 1. Initially, I thought I could add 11, and then I realized no, adding 11 doesn't work. So here's the program. We start out with the initial value of 1 and set up a do loop that covers 10 elements. We take our input number, duplicate it, convert it from single to a double, and then print it out in a field 14 digits wide. So that lets us look at our input number. And this is using that u.comma.r, which gives us a formatted number with commas for ease of reading. Then we duplicate our input number and we square it. And now we use the double number print to show what our product is. And then increment. Remember, the increment is by multiplying by 10 and adding 1 in loop. So this gives us 10 different displays. Then at the bottom, I wanted to look at it without the commas. So the 1 minus backs out the 1 and 10 divide restores us back, offsetting the increment that was just done. So we'll relook at the last value and we square it and then print it out. And this uses the plain old d.r, which gives me a double number right justified in a field 39 digits wide. And that gives us a check at what's it look like without all the commas. So here's the result. And sure enough, 11 squared is 121. 111 squared is 12321, and so down the line. And it progresses until we have 9 ones in a row. And we come out with, and bless Win32 because it handles double numbers quite nicely. And so we are somewhere in, I don't know, the 10 quadrillion, big long number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, 7, 6, 5, 4, 3, 2, 1. And then down below, we have the same number printed out, mostly for beauty, where we can see the progression of digits without the commas. And thus, the conjecture has been proven. Do we have any comments? This is hardly earth-shaking math, but it's kind of interesting to take it off of a restaurant table and bring it into the fourth world.
Yes, I've got a question.
Go ahead.
Can people hear me? You are trying to do multiplication to solve this problem?
Yes.
You could solve the problem just by pure addition, right?
You don't have to ask the question because my answer is no. I don't see how to do it by pure addition.
Okay, so you
I can maybe by shifting and adding, but I don't see pure addition.
So what you do is let's say 11 times 11. That's the equivalent of 10 plus 1 times 11, right?
Yes.
So when you multiply by 10, you really only have to add a 0 to the 11, and then you add the 1 times the original thing, and you get 121. So by basically adding a 0, replacing the left-hand side of the number, whether it's 11 or 111 or one of those, with a series of 1,000 plus 100 plus 10 plus 1, and then just doing a shift to add a 0 and then adding everything, you end up getting this sequence of numbers that go 1, 2, 3, 2, 1.
How do I add a 0? Well, how do I shift to add a 0?
I'm not talking about the math. I'm just looking as a grade schooler by saying I'll put a 0 in back of the number, shift it over, and start adding.
Let's look at it two ways. To add a 0 in a binary in a numeric fashion, you multiply by 10, and so that adds a 0 on the right hand side. Now, some math has done in the symbolic notation, where instead you are looking at this as a series of ASCII integers, ASCII characters. In the case of doing it with ASCII characters, then you could do a left shift, opening up one character position, and then append a new 0 as an ASCII character. So, the shift and add could be done in ASCII form with symbolic processing, or you multiply by 10 and add 1 to do the shift and add in numeric processing.
Yeah, I guess what I guess what I'm saying is the symbolic solution to this thing is trivial, but if you want to start putting numbers into registers and operating on them, then it gets very complicated. So he did using the numerics, and I'm saying symbolically, it's a trivial thing to solve.
Years ago, when the cryptography came along using huge numbers and multiplying huge numbers together, I think one of the methods they were using was symbolic multiplication, where they would not treat these as numbers, but they would treat them as a sequence of symbols, and they could do an n-digit multiplication symbolically. But I never investigated.
Multiplying by 10 is two shifted and add, isn't it?
That's correct. That's what we did.
Well, Forth is very wedded to manipulating integers. In particular, banks are interested in manipulating large strings, large infinite precision strings of integers. I guess there was an infinite precision math package that somebody wrote back in the Cogswell days and did a talk. That was sort of pre-YouTube, but instructive nonetheless. We've gone off into the weeds, it seems. Thank you, Bill. Any quick questions? Anything additional? Okay. I'm going to mute Mr. iPhone because he is just background noise at this time. Some ne'er-do-well. So as Chief Ne'er-do-well, Bill, you done? He's
All
muted,
done. Thank you.
Okay. Sometimes it isn't clear to someone of my limited intellect. I didn't want to cut anybody off prematurely. Brad will introduce himself and tell us about infixing Forth.